Last episode you learned calculus, the derivative, the chain rule, and autograd computing gradients automatically. That tells you how the network adjusts its weights. But adjusted toward what exactly?
The answer is the loss function. And the most common loss function for classification, cross-entropy, is not a random default. It is the mathematically correct choice. This episode shows you exactly why. To understand cross-entropy, you need two ideas from probability. Entropy, which measures uncertainty, and KL divergence, which measures how far two distributions are from each other. I'm Mahaz. Let's build the loss function from the ground up. Today, probability distributions, information content, entropy, KL divergence, cross-entropy derivation, softmax, negative log likelihood, and a full NumPy walkthrough at the end. Everything starts with a probability distribution, a function that assigns a probability to every possible outcome. Discrete distributions assign probabilities to a finite set of outcomes. Roll a fair die. Each face gets probability 1/6. A neural network classifier outputs a discrete distribution, one probability per class, all summing to exactly 1. Continuous distributions spread probability over a continuous range. The Gaussian, or normal distribution, is the most important one in deep learning. Its bell curve shows most values cluster near the mean. Two distributions matter constantly throughout this series. The true distribution P, the real labels in your dataset, and the predicted distribution Q, what your model outputs. The loss function measures how different Q is from P.
This is the whole game. Train the model until Q matches P as closely as possible. Every loss function is a different way of measuring that mismatch.
Before KL divergence and cross-entropy, we need one idea: information content.
The information content of an event is how surprised you are when it happens. A very likely event, say, the sun rising tomorrow, carries almost zero information. A very unlikely event carries a lot. Formally, the information of event X is negative log base 2 of P of X. The negative log is large when P is small, and near 0 when P is near 1. The log base 2 gives us bits as the unit. The entropy H of P is the expected information, the average surprise across all outcomes. It is the sum over all X of negative P of X times log P of X. High entropy means the distribution is spread out and uncertain. Low entropy means it is concentrated, confident. A uniform distribution over 10 classes has maximum entropy. Every outcome is equally likely, so nothing is predictable. A one-hot distribution has zero entropy. One class gets all the probability, and the outcome is completely certain.
Now we can measure how different two distributions are. This is KL divergence.
The KL divergence from Q to P, written DKL of P double bar Q, measures how much extra information you need to describe samples from P when you use Q as your encoding scheme instead of the true P. Formally, the sum over all X of P of X times log of P of X divided by Q of X. It is always 0 or positive, 0 only when P and Q are identical. It is not symmetric. KL from Q to P does not equal KL from P to Q. Minimizing the KL divergence between the true label distribution P and the model's predicted distribution Q is the goal of training a classifier. And here is the key step. Expand the KL formula, and part of it is exactly the cross-entropy between P and Q. Specifically, KL of P from Q equals cross-entropy of P and Q minus entropy of P. Since the entropy of P does not depend on the model's parameters, minimizing KL is identical to minimizing cross-entropy. That is why cross-entropy is the correct loss.
Now the derivation. Cross-entropy loss, derived from first principles.
Cross-entropy of P and Q is defined as the negative sum over all classes of P of X times log of Q of X. For a one-hot true label, where P is 1 for the correct class and 0 for all others, this collapses to just negative log of Q at the true class. So for a 3-class example where class 0 is correct and the model outputs probability 0.8 for class 0, the cross-entropy loss is negative log of 0.8, which is about 0.22. Low loss. The model is nearly right. If the model only gives 0.1 to the correct class, the loss is negative log of 0.1, about 2.3. That's 10 times higher.
The log makes the penalty grow very steeply as the model becomes more confidently wrong.
This steep penalty for confident wrong predictions is exactly what we want. A model that says 99% probability to the wrong class should be punished far more than one that says 60%. The log function enforces this naturally.
Cross-entropy needs a proper probability distribution as input, values between 0 and 1, summing to 1. That's what Softmax does.
The final layer of a classifier outputs raw scores called logits, any real numbers, not probabilities. Softmax converts logits into a probability distribution by taking the exponential of each logit and dividing by the sum of all exponentials. Example, logits are 2.0, 1.0, 0.1. The exponentials are roughly 7.39, 2.72, and 1.11. Sum is about 11.22. Softmax probabilities are 0.659, 0.242, and 0.099. All positive, all summing to 1. The exponential does two things. It makes every output strictly positive, and it amplifies differences. The highest logit gets disproportionately more probability, making the distribution sharper than the raw logits suggest. In PyTorch, never apply softmax manually before cross-entropy loss. The nn.cross-entropy loss function expects raw logits and applies log softmax internally in a numerically stable way. Applying softmax first causes numerical instability and wrong gradients.
Cross-entropy and negative log likelihood are two names for the same idea, seen from different angles.
From a statistics viewpoint, given a dataset, find the model parameters that maximize the probability of observing that data. This is maximum likelihood estimation, or MLE. The likelihood of the entire dataset is the product of probabilities of each individual example. Products are hard to optimize, so take the log. The log likelihood is a sum. Then negate it to turn maximization into minimization. That gives you negative log likelihood. For a one-hot classification problem, the negative log likelihood for a single example is exactly negative log Q at the true class, which is exactly the cross-entropy formula we derived. They are the same thing, from two different starting points. This tells you something important. Cross-entropy training is doing maximum likelihood estimation. You are finding the parameters that make the observed labels maximally probable under your model. That is a principled, statistically justified goal.
Let's compute cross-entropy from scratch in NumPy. No PyTorch, no shortcuts.
Step 1. Define logits and the true label. Logits are 2.0, 1.0, 0.1. True class is 0. Step 2. Compute softmax. Subtract the max first for numerical stability, then exponentiate and normalize. Step 3. Extract the probability of the true class. That's the first element of the softmax output. Step 4. Compute the cross-entropy loss, negative log of that probability. Running this code gives us a loss of about 0.4076. Our model gave class 0 a probability of about 0.659, so the loss is relatively low. The model is fairly confident and correct. Change the true label to class 2, the lowest probability class, and the loss jumps to about 2.31. That steep increase is the log penalty. Cross-entropy punishes confident wrong predictions hard.
3 common probability mistakes that break training, and how to spot each one instantly.
Bug 1. Applying softmax before nn.cross-entropy loss. PyTorch's cross-entropy loss already includes log softmax internally. Applying softmax first means you apply it twice. The loss gets incorrect gradients and training silently fails. Bug 2. Using MSE loss for a classification problem. MSE treats class labels as continuous values. Class 0 and class 2 are not two apart in any meaningful sense. Always use cross-entropy for classification targets. Bug 3. Forgetting that cross-entropy expects raw logits, but binary cross-entropy with logits also has a separate version. nn.bc with logits loss for binary, nn.cross-entropy loss for multi-class. Using the wrong one silently produces incorrect gradients. The fix for all 3. Check your loss function's documentation for what it expects, logits or probabilities, and verify by printing the loss value in epoch 1. A loss near log of number classes means your model starts at near uniform, a good sign.
Before episode 7, run through this checklist.
Check 1. You can explain what a probability distribution is and the difference between discrete and continuous. Check 2. You can define entropy and explain what high versus low entropy means for a classifier's output. Check 3. You can state what KL divergence measures and why it is not symmetric. Check 4. You can derive the cross-entropy loss formula from the KL divergence expansion. Check 5. You know what Softmax does, why it is needed before cross-entropy, and why you must not apply it manually in PyTorch before cross-entropy loss. Check 6. You understand that cross-entropy training is maximum likelihood estimation. 6 checks. All pass. You are ready for episode 7, the perceptron, the biological neuron, and building a single neuron from scratch in NumPy.
Recap. What you now have before episode 7.
A probability distribution assigns probability to outcomes. Entropy measures average surprise, how uncertain a distribution is. KL divergence measures how far two distributions are. Minimizing KL is equivalent to minimizing cross-entropy because entropy of the true labels is a constant. Cross-entropy loss for one-hot labels is just negative log of the predicted probability at the true class. Softmax converts logits to probabilities. Never apply it before cross-entropy loss in PyTorch. Your challenge. Compute cross-entropy by hand for logits 2.0, 1.0, 0.1, and true class 0. Then verify in NumPy. Post both results in the comments. Cross-entropy was never a random default. It is KL divergence with the constant terms removed. It is maximum likelihood estimation for a classification problem. It is the only sensible choice.
Every time you write cross-entropy loss from here on, you will know exactly what mathematical object you are minimizing and exactly why it works.
Next episode, the perceptron, a single artificial neuron, from the biological inspiration through the math, all the way to a working implementation trained from scratch in NumPy.
Subscribe. Post your cross-entropy calculation. See you in episode 7.